Hey Heather, so starter, you know the script, pause the video, complete the questions, and then unpause it and I'll go over the answers. So, question 1, why don't soaps work well in hard water? Nice and easy, they form a precipitate, and you should know that precipitate, that's a scum. Okay, so they're forming a scum. What do we use instead? In places of hard water, we can use detergents. Yes, soapless detergents. Okay. Question 2, what is meant by an emulsion? An emulsion is a mixture of two or more immiscible, okay, that's a key word there, two or more immiscible liquids. Okay, that's liquids that don't dissolve in each other, for example, water and oil. Okay, and question B, 3A, sorry, what is added to an emulsion to ensure mixing? We would add an emulsifier. Okay, very important, emulsifier. Now, what two components are reacted together to form an emulsifier? Again, you need to know this. It's an edible oil and glycerol. Okay, and remember, when we react a edible oil with glycerol, only one or two of the hydroxyl groups in glycerol are reacted. Okay, we tend to have usually one OH left, and that acts as your sort of polar head. Okay, question 4, explain fully how soaps can be used to clean dirt found on your hands. I'm not going to write that out, I'm just going to show you the answer here. So you've got a non-polar hydrophobic tail of the soap molecule that's dissolving into the dirt, and the polar hydrophilic head that dissolves into the water. Okay, diagrams go a long way. Remember, if you are doing the head and tail, make sure the tail is right into the soap. Yeah, it's flush to the dirt. The negative polar heads, once we start to agitate them, they repel each other and they form small droplets called micelles. Okay, these micelles are negatively charged, so they repel each other, and this keeps the dirt suspended in the water. Okay, that's how it's suspended, and obviously when it's suspended we can easily wash it away. Okay, so that's what you needed. Diagrams, get the information and get the diagrams in, it goes such a long way. Okay, right, so our lesson today, we're going to be moving on to fragrances and skincare. Okay, so first things first, we're going to talk about something called essential oils. Essential oils. Okay, now I do want to make it clear now that it doesn't mean vital. Okay, it comes from the word essence. Okay, so essential here is talking about the essence. I'm just making another wee side note here, and this is important. You don't want to mix this essential oil up with essential amino acids. Okay, they don't mean the same thing. Do not mix up with essential amino acids. Now remember, essential amino acids are amino acids that the body can't make. Essential oils do not mean oils that the body can't make. So it's very important that we do not mix essential oils and essential amino acids up. So I'll give you a wee sort of background to what essential oils are, and then we'll start looking at how we extract these essential oils. Now, first things first, they are hydrophobic. Okay, it should make sense because there are oils, yeah, oils are non-polar, so that's going to make them hydrophobic. So they are hydrophobic, which means they are non-water soluble. Okay, and that's making them non-polar. So that's very important. I'm going to highlight that. So they are hydrophobic, non-water soluble. That means that they're non-polar, and it makes sense because there are oils, and oils are non-polar. Okay, so they are hydrophobic liquids containing mixtures of volatile. Now we've came across this word before, volatile aroma compounds. Okay, and again that's something you can get asked about. They are very volatile. Okay, and that's important that they're volatile, because obviously when we start looking at the uses you'll understand why. But yeah, they're hydrophobic, non-polar, volatile aroma compounds. Okay, and what we mean by volatile, we've already spoke about this, but it means they evaporate easy in air to give distinctive fragrances. Okay, so example of these fragrances could be lavender, peppermint, orange, lemon, etc, etc. Okay, so you need to know what an essential oil is. Hydrophobic, volatile aroma compound. Okay. Right. So essential oils are extracted from plant material by steam distillation. Okay, steam distillation. And usually at this point there's a wee experiment that you guys do in class to extract sort of the essence of orange from orange peel, but unfortunately we can't do that. However, I am going to draw out the experiment for you. Okay, so just to get you an idea of what's happening. So we're going to do draw a test tube, okay, and then coming from that test tube we're going to have a delivery tube. Like so, and that is going to come down into a beaker. Okay. Like so. Right, now obviously there's a few things we need to add to this. We need to add our stopper so that the sort of essence doesn't escape, and there's a few things we are going to add to this. Okay, so in the test tube we're going to have sort of three layers. Okay, now the first layer, I'm going to highlight this in yellow. Okay, and we'll label that. That will be ceramic wool soaked in water. Okay, so that mineral wool, we soak it in water that's what that's going to be. Okay, then on top of that, in this one, okay, just going to highlight this orange. That is just going to be normal ceramic wool or dry ceramic wool. Okay, so dry ceramic wool. And on top of that, I'm just going to put an X. Okay, and I'll highlight that pink. And that X is your sort of plant material. Okay, so in the sort of experiment we would do in the class, that plant material would be orange peel. Okay, now what we would do in this experiment is we would add heat. Okay, and I'll just make that orange for heat. Okay, now we need to add a couple more things, and I'll talk about the experiment. We need to add a wet paper towel. Okay, and hopefully you're realising why we're adding a wet paper towel, and that's because it acts as a condenser. Okay, it's acting as a condenser. Now, what's going to happen here? So we've got ceramic wool soaked in water, we've got dry ceramic wool, and then on top of that dry ceramic wool we've placed some orange peel. So we're going to start heating this up, and then the water here is going to evaporate, okay, and the evaporation it turns into steam, hence the word steam distillation. Okay, so it's going to turn into steam, and then the steam is going to pass over the orange peel. Okay, and by passing over the orange peel, that's going to extract the essence of that orange peel. Okay, so what's going to happen is both the essence of the orange peel and the steam is going to go along the delivery tube, and then it's going to hit this point, and then because it's the wet paper towel, it's going to condense back. So the water is going to condense. Okay, the steam will condense back into liquid water, and then on top of the water, because it will be an immiscible liquid, you're going to get your essential oil. Okay, which is going to be your essence of this orange peel. Now, obviously, just make a wee note here. You are very much like with esters. You are getting 2 layers, since the liquids are immiscible. Okay, you're getting 2 layers since the liquids are immiscible. So let's summarise that. Summary. So essential oils are extracts of the volatile, and that's a key word, yeah, volatile aroma composed from plants. Okay, and remember what we spoke about, they are non-polar, okay, and because they're non-polar, that makes them hydrophobic. Okay, and also the essential oils consist of something called terpenes and terpenoids. Okay, now we haven't spoke about this before, so we'll be next sort of page we'll be talking about what terpenes are, what terpenoids are. So essential oils, they're made up of these terpenes and terpenoids. Okay, now very important that you don't mix up essential oils with edible oils. Okay, edible oils, we obviously we did when we spoke about fats and oils, yeah, edible oils and oils. So an example of an edible oil would be olive oil, yeah, for cooking. And they are made up of triglycerides. Okay, we spoke about that. Triglycerides, we're talking about the three ester links. Okay, the three ester links, and you've got the long chain, obviously, fatty acid part. Yeah, and just a wee note, emulsifiers can combine with glycerol to form emulsifiers. So very important that we don't mix these two up. Yeah, that's one thing, and then edible oils are a completely different thing. Similar, obviously, but different. Right. So what we're going to do now, we're going to look at uses of essential oils. Why are we talking about essential oils? What are their purpose? So essential oils are used in perfumes. Yeah, they can be used in cosmetics. They can be used in soaps. Okay, it doesn't change the sort of structure of the soap or the function of the soap. It literally, we add essential oils to soap to give scent, to give them a scent. Okay, just to make them smelling nice. It doesn't alter how they work or the structure of them. It's literally just to give them a smell. Okay, essential oils are also found in flavourings, in food and drink. Okay, there are many more, but they're probably the main ones. So on the previous page we spoke about terpenes. Okay, so essential oils are made up of these molecules called terpenes. I also said terpenoids, but don't worry, I'll come back to that. So terpenes are the most common compounds found in essential oils. Okay, very important are terpenes. Now, how are terpenes made? Let's talk about that. So terpenes are made by joining isoprene units together. Okay, so very important that I'm going to highlight that. So terpenes, okay, so terpenes are found in essential oils, and terpenes are made by joining isoprene units together. Now, what's an isoprene unit? I hear you ask. We'll get onto that, don't worry. Okay, now, just as a wee extra bit, now it probably makes sense here, but we'll write it out. So 2 or more isoprene units chemically joined together are called terpenes. Okay, so one isoprene unit on its own, not a terpene. 2, 3, 4 or 5 chemically joined together, that's a terpene. Okay, so we need to look at what an isoprene unit is first of all. Okay, so what is an isoprene unit? Now a lot of new definitions coming in here, a lot of new chemicals, so it is important obviously once we've done this to go over your notes. Now, an isoprene unit looks like this. Okay, now don't worry if you're like, what the hell's that? I will go into detail about it. However, how I remember this, okay, and this has stuck with me for sort of years, is if you look at this, okay, and you're probably going to think I'm horrible, but I've never forgotten it, okay. This here looks like a dog with front legs chopped off, okay. Now I'm not horrible, okay, but if you think it, that's the dog's back legs, that's its tail, okay, that's the body, and the two up here, that's the ears, okay. And what you notice? There's no front legs. The dog's legs have been chopped off, okay. So that's how I remember what an isoprene unit looks like. Now, you can be asked to draw out the isoprene unit in full. Now we have spoke about this at Nat 5, not in a lot of detail, but this is something called the skeletal formula. Now if we look at this, at each sort of point, so there's a point there, there's a point there, there's a point there, there, and there. Okay, so at each point, that represents a carbon. Okay, so if we draw this out again, yeah, we've got a carbon here, and then we've got a double bond. Okay, that's what those two lines represent, a double bond going up to another carbon, and then a single bond going up there, and then we've got the body part going to another carbon, and then we've got the ears, double bond going up to another carbon. Okay, so that's what that looks like, and then all you would need to do is fill in the hydrogens. Okay, so we've got one carbon here, 2 bonds are already used up, so that means 2 hydrogens can fit there. Okay, that carbon, all 4 bonds are used, so there's no hydrogens. This carbon, only 1 bond used, so we've got 3 hydrogens here. This carbon, we've got 3 bonds, so we've only got 1 hydrogen, and then that carbon has 2 bonds used up, so that's space for 2 hydrogens. Okay, so that's how that sort of skeletal structure fits into that. Okay, now if we were to draw this out like we would a normal molecule, like on like a linear fashion, we would have this, so we would have 1 carbon, double bond, 1 carbon going up to a branch, 1 carbon, double bond there. Okay, so all I've done is I've taken this structure and I've just laid it out like this, and if I was to fill in the hydrogens, like so. Yeah. Oh, sorry. That hydrogen shouldn't be that. So yeah, that's what an isoprene unit looks like. Okay. Now you can be asked to give the systematic name of this isoprene unit. Now you can either draw it out and then name it that way, or probably for the best is just memorise it. Okay, so if we look at this, we're going to start from the side closest to the functional group and the branch. So this is carbon 1, carbon 2, carbon 3, and carbon 4. Okay, we've got a branch on carbon 2, and we've got a double bond between carbon 1 and 2, so we choose the lowest number. Yeah, between 1 and 2 we choose 1, and also we've got a carbon to carbon double bond between 3 and 4, so we choose the lowest number, which is 3. So if we name this, what we've got is 2-methyl yeah, because we've got a methyl branch on carbon 2, so 2-methyl bute, because the longest chain is 1, 2, 3, 4 bute, and we've got a double bond between between carbons 1 and 2 and 3 and 4, so this is 2-methyl bute 1, 3 dash diene. And the reason it's di is because we've got 2 carbon to carbon double bonds. So this is 2-methyl bute 1,3 diene. Okay, and that is the systematic name. Let me just put that in brackets. This is the systematic name for an isoprene. Okay. So for terpenes, the formula is going to be C5H8 because each isoprene unit has 1, 2, 3, 4, 5 carbons and 1, 2, 3, 4, 5, 6, 7, 8 hydrogens. So the formula for a terpene is going to be C5H8, where N is 2 or greater. Okay, because remember, a terpene is when we've got 2 or more isoprene units joined together. Okay. Right, we're getting to the end. So let's look at examples. The terpene myrcene consists of 2 isoprene, sorry, I should have joined them up, isoprene units joined head to tail. Joined head to tail. Okay, now sometimes isoprene units can join head to tail, and you'll see what I mean when I draw it. They can also join as a ring structure, and again you'll see that when we start looking at examples. Okay, so terpene myrcene consists of 2 isoprene units joined head to tail. Okay, so if I draw this, it's quite difficult to draw. I don't like drawing this. So we've got CH3, and then that goes up to a C, and then that branches off to a CH3. Okay, then we've got a double bond to a CH, and then that goes up to a single bond H2, and then that CH2 goes down to another CH2, and that goes up to a C with a double bond CH2, and then that goes down to a CH, and that goes double bond up to a CH2. Okay, so that's what myrcene looks like. Now you're not expected to memorise that, okay? You just need to be able to recognise how many isoprene units are there. Now, if we look at this, okay, we're just going to count the carbons. So we've got 1, 2, 3, we're not numbering the longest chain, we're just counting how many carbons there are. So 1, 2, 3, 4, 5, okay? So what we can say is, highlight this, this first section, okay, where it's got 5 carbons, that is 1 isoprene unit, okay, and then the next one we've got 1, 2, 3, 4, 5, okay, and if we do that in an orange colour, that there is your other isoprene unit. Okay, so this molecule's made up of 2 isoprene units. So 2 isoprene units. So if we go back to our formula, which is C5H8N, yeah, in this case, because we've got 2 isoprene units, N equals 2, therefore the formula, the molecular formula, equals C10H16. yeah, because we're literally just times the 5 by 2 to get 10, the 8 by 2 to get 16. Now if we count that, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 carbons, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 hydrogens. Okay? So, we note here, we're going to look at what a terpenoid is, but I'll give you this wee note first. So terpenes can be unsaturated. Yeah, they can be unsaturated hydrocarbons, or can contain oxygen. Okay, and then in brackets, due to being oxidized. Okay, so terpenes can be unsaturated hydrocarbons like this one here. Yeah, it's unsaturated, it's containing carbon to carbon double bonds, or it can contain oxygen. Okay, because it's been oxidized. Now, oxygen containing terpenes are called terpenoids. Okay, you need to know that. So any terpene that contains oxygen or has been oxidized, so it's containing oxygen, is called a terpenoid. Okay, so what do you call an oxidized terpene? A terpenoid. So again, very important that. Now, also very important is you need to be able to identify how many isoprene units that are found within a terpene, like what we did here. Okay, we drew out a terpene and we identified that there was 2 isoprene units. Okay, so you need to be able to identify how many isoprene units are found within a terpene. Okay, remember a terpene is when we've got 2 or more isoprene units chemically joined together. Now, a wee hint, okay, it's very easy, is literally all you want to do is divide number of carbons by 5. Okay, you'll see what I mean here. You'll see what I mean. So if I draw, I'm just going to draw the skeletal structure. Okay, remember we spoke about what the skeletal structure was roughly. Okay, now remember what I said, that every sort of point represents a carbon. So 1 point, so 1 carbon, 2 carbons, 3 carbons, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, sorry, I've missed a bond there, 15. Okay, so here in this molecule we have 15 carbons. Okay, so if we divide, obviously there's 5 carbons in 1 isoprene units, so if we divide 15 by 5, that means we've got 3 isoprene units. Nice and easy. Okay, so if 1 isoprene unit is 5 carbons, 15 carbons must be 3 isoprene units, and that's it. Okay, literally that's it. Now let's do more. So let's count how many carbons we have. So we've got a carbon here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 carbons. Okay, so 10 carbons, nice and easy. So 10 carbons divided by 5, we have 2 isoprene units. And guys, that's it. Okay, let's do one more. Let's see if we can do one more. So one, let's So let's count this. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 carbons, and then obviously that last carbon there is bonded to that hydroxyl group. So we've got 10 carbons. So again, that means we've got 2 isoprene units. Now because this terpene contains oxygen, what do we call it? We call it a terpenoid. Okay, because it's containing oxygen, it's a terpenoid. And guys, that's it. Okay, so if we go back to the start, okay, you need to know what an essential oil is. Please do not mix it up with an essential amino acid, completely different. Yeah, essential oils, hydrophobic, yes, so they're non-polar and they're volatile. They evaporate easily, and that makes sense knowing what we know. Yeah, how they're used in perfumes, how to give soaps scent. We want them to be volatile so that they evaporate and the scent goes into our nose and we smell it. Okay, so hydrophobic, non-polar, they're volatile aroma compounds. Okay, they're extracted from the technique steam distillation. Okay, and that's the experiment there that you would have done in class. Okay, so we're heating it up, converting the water into steam. The steam passes over our plant material and that extracts the essential oil. Okay, don't mix up essential oil and edible oil. Yeah, essential oils are all to do with the aroma. Edible oils, obviously we eat them, they're used in cooking, for example olive oil. Yeah, and obviously edible oils can form emulsifiers. The uses, obviously we spoke about the uses already: perfumes, cosmetics, soaps to give scent, and essential oils are made up of these compounds called terpenes. Okay, now terpenes are made up of 2 or more isoprene units joined together. Now you need to know what an isoprene unit is. Yeah, it's got 5 carbons, 8 hydrogens. You need to know how to draw it. Okay, so you can think of the whole dog with the front legs chopped off, but you also need to be able to draw it out. Okay, and name it, give this systematic name to it: 2-methyl-but-1,3-diene. You can simply get asked, what is the systematic name of an isoprene unit? Okay, and you need to know it. Okay, terpenes, that's the formula. Yeah, C5H8, N simply is just 2 or greater. And then finally, you need to be able to identify how many of these isoprene units are found within a terpene. Okay, so again, 10 carbons, divide by 5, we've got 2 isoprene units. Yeah, 15 carbons, divide by 5, we've got 3 isoprene units. Yeah, and then finally, a terpene unit that's been oxidized or containing oxygen is called a terpenoid. Okay, so there's a lot of new information going on there, so make sure you're up to speed with it. Okay, right, that's us, so thank you very much.